Hello.
Okay, so we are going to talk about slope fields today.
Hey, you know what? Sure.
So, if you look at the two sheets that I gave you, the first sheet we have a series of slope fields, or we actually haven't created the slope fields yet, but we're going to draw some slope fields on this paper. And it says draw a slope field for each of the following differential equations. Each tick mark is 1 unit. Now, the assignment I gave you over the weekend, I said it's really, really important assignment because those are questions that are like the ones that could be on the AP Calculus exam in May. In fact, those were two questions that were from past AP Calculus exams. If I were guessing what percent chance that an area and volume problem would be on the AP exam as a free response, I would say 100% chance. Oh, really, I can't think of a year that they haven't had an area and volume problem as the free response, on the free response portion. Now, I haven't done the statistics as far as how many slope field problems are on the free response portion, but just from experience and looking through years and years and years of old AP Calculus exams, if I were guessing about what percent chance a slope field problem will be on there, I would say probably around 80. So still a pretty high chance, but it's not one that they throw on every single year. Most years you will see a question like this, but on the back of this sheet, these two examples are examples like what you might see on the AP Calculus exam. These are not actual questions from the AP exam. They're just there for you to practice. But the second sheet I gave you that's like number 75, I think. Did I give you that second sheet?
Yes.
Okay. That is an actual AP Calculus exam question from the AP exam at the end of the year. All right, so big picture. I'm going to give you a differential equation. Remember, differential equation just means that this is y prime, and you want to figure out what y is, the original equation. There's two ways that you've learned how to do that. You can either just take the antiderivative, as in the case of number 1, or sometimes it's harder, and you have to do separation of variables. Get all the x's on one side, y's on the other side before you take the antiderivative. Those are all things that we've talked about before. So what we haven't talked about is how to create a slope field. And that's what we're doing today. So on number 1, I'm telling you that y prime, or dy by dx, is x plus 1. So what you're going to do is you're going to take each one of these points that you see plotted on this graph, and you're going to figure out what is the slope at that particular point, simply by subbing into the derivative. Once you know what the slope is, you're going to draw a little tiny line segment through that point that is representative of the slope at that point. In other words, if I start in the top left-hand corner, that is the point, what, -3, +2? So at the point -3, +2, what is the slope? Well, to find the slope, you just substitute into the slope formula, or dy by dx. You put -3 in for x. -3 plus 1 is -2. So we're going to draw a tiny line segment with an estimated slope of -2 through that point. So do that with me right now. -2 is just going to be a little bit steeper than -1. Eyeball it. It doesn't have to be perfect. It does have to be in the negative direction. But try to eyeball what you think -2 slope would look like. And just a little tiny line segment through that point. Well, if we know the slope through -3, 2 is -2, then can't you also say that anything with an x value of -3 is also going to have a slope of -2? So anything in this column, it's not really a column, but anything in this first set of order pairs is going to also have -2. So try to mimic that -2 for all of those points. All right, let's move on to the next column of points. We have the point -2, +2. What would be the slope through the point -2, +2? -1, because you're just going to substitute in the x value. -2 plus 1 is -1. So now we're going to try to draw a line segment that has slope -1. It should just be the diagonal. It should be a little flatter than your -2 that you just drew. And in fact, you can go ahead and draw that -1 slope for all of the points that have an x value of -2. Are you following me so far? Any point that has an x value of -3 has a slope of -2. Any point that has an x value of -2 has a slope of -1. So these should all look similar. Anything with an x value of -1 should have a slope of what?
0.
0. What does slope of 0 look like? Just a horizontal line through all of those points. Okay, what about anything that has an x value of 0? +1. So try to make it symmetric to the points that you plotted, or the slope that you plotted on the points where x was -2. So try to do a slope of +1. Again, it doesn't have to be perfect, just try to do the best you can freehand. What about when x equals 1? All of these points, x equal 1. 2, so you're going to make it a little bit steeper. Where x equals 2, so a little bit steeper, but in the positive direction. And last, where x equals 3?
5.
No. 4. So again, these don't have to be perfect, but you want to just try to kind of eyeball it and do the best you can. So what this represents, this is our slope field for that particular differential equation. And so if we actually find the equation, this one's, I picked an easy example to start with because we only had to worry about the x coordinate. And also, if we want to find out, if this is y prime, and we want to find out what y is, all we have to do is take the antiderivative. You don't even have to separate variables, really. Just take the antiderivative of x, 1/2 x squared, or x squared over 2, plus x, plus c. What does this graph look like? Well, what does this graph look like? It's a parabola that opens up. Can you talk to me about the vertex? Do you remember the vertex formula from Algebra 2? -b over 2a. So the opposite of 1 over 2 times the half is 1. So it's the vertex going to be at x equal -1. Well, when you add c, that just means a shift up or down. So can you see how this could actually look like a parabola with vertex at -1? But this one would be one of the graphs, and then if you shifted it, you could get another graph. Depending on what C is, that's where the parabola would be placed on that slope field. Just trying to give you an idea of the big picture. Okay, so I think so too, but my definition of cool usually doesn't fit with everyone else's. Again, this is an easier example. I wanted you to be able to kind of see it, but also it only involved x, and we didn't have to do the whole separation of variable thing when we were finding the original function and whatnot. Let's move down to number 3, because number 2 is only dependent on y, so that's kind of boring. But you're going to have to come back and do each one of these for me for homework. But we're going to do number 3 together. Like how I slid that in there on you. We're gonna do number 3 together. So this time, let's look at, I always start in the top left-hand corner, but you can start anywhere. This is the point -3, +2. The slope is x plus y. So what's -3 plus 2? Hello? -1, yes. Are you awake? Wake it up. Okay, what about -3, +1? -3 plus 1, -2, so make it a little bit steeper. -3 plus 0, -3, make it a little bit steeper. Now, you know, our little line segments aren't going to look exactly the same. That's understandable. But one way to help you is notice how I kind of set my mark here at -1. Like if I use that first point as a reference, then I know to make this one a little bit steeper, that one a little bit steeper, and I can kind of always go back to that first slope and judge it. All right, what about -3, -1? That's going to be -4, and -3, -2 is -5. And then we have -2, +2, which is 0. -2, 1 is -1. -2, 0 is -2. -2, -1 is -3. -2 is -4. Then we do -1, +2. That's going to be +1. So try to kind of mimic what you did for -1, but go in the positive direction. -1, +1 is 0. Can we go ahead and put all of our zeros on there? If you see a pattern, it's okay to go ahead and put those on there. Like we're going to have a 0, 0 here. We're going to have 1, -1 will be 0 here. 2, -2 will be 0 here. You can go ahead and put your zeros on if you want to. -1, 0 is going to be -1. Then -1, -1 is -2. Then -3. Then 0, 2 is going to be 2. 0, 1 is going to be 1. 0, -1 is -1. And then we have -2. Here we have 1, 2, which is 3. 1, 1 is 2. 1, 0 is 1. 1, -2 is -1. Then we have 2, 2, which is going to be 4. 2, 1 is 3. 2, 0 is 2. 2, -1 is 1. Then 3, 2 is 5. 3, 1 is 4. 3, 0 is 3. 3, -1 is 2. 3, -2 is 1. What do you think is happening on this graph? Sort of looks like there might be a slant asymptote here, huh? Can you kind of see that? Like the direction it's tending towards this diagonal line here? So it looks like there could be a slant asymptote. But let's go ahead and find the original equation to kind of see what we're working with. So we have, to do this on another sheet of paper so I have enough room. We start off with dy by dx equals x plus y, and I want to find the original function. Good. First thing you want to do is separate your variables. So we can move our negative y over here and multiply our dx to the other side, and then integrate both sides. Everybody okay with me putting my integral here in between the negative and the y so that my negative's on the outside? Because it's just like a constant -1. So negative y squared over 2 equals x squared over 2 plus c. Then you're going to multiply both sides by -2. When you multiply the right-hand side by -2, the 2's cancel, but you still have a negative x squared. And then minus 2c is still just c. And then we take the square root of both sides. So y equals plus or minus the square root of negative x squared plus c. Now let me say this about the plus or minus. Usually it will depend on the point that you're passing through. Like eventually, here in a minute, we're going to talk about particular solutions where we have to figure out what c is. And then wherever the point c passes through, usually that determines whether you use the positive or the negative square root. But we'll actually get to look at a good example of that in a minute. So this will be the general solution. The particular solution, you would have to choose either plus or minus, depending on which, what your initial condition is. Okay. Flip it over to the back. Number 7 is the one I want us to look at. This is a question written like an AP free response question. Remember, those questions are normally worth 9 points. You usually have 6 of them on the AP Calculus exam, 2 calculator and then 4 non-calculator. This one, I believe, was designed to be a calculator problem, but it could go either way. Sometimes you'll see these questions on calculator, sometimes non-calculator, but this one I believe was on the, or it wasn't actually on the exam, but it was designed to be like one on the exam that's a calculator problem. All right, let's look at part B on number 7. Because I'm confident that you guys can now graph a slope field. Is that fair to say? You could do a slope field since we've done 2 examples together. Yes? Okay. So we're going to look at 7b. Let f be a function that satisfies the given differential equation. Write an equation for the tangent line to the curve y equals f of x through the point 1, 1. Then use your tangent line equation to estimate the value of f of 1.2. Tell me the key words in that big paragraph. Equation for the tangent line. Those words should jump off the page and just smack you right in the face when you see those words. And what do they tell you to do when they smack you in the face? What are you supposed to write down?
Y minus y1.
Thank you. Perfect. Y minus y1 equals the slope times x minus x1. When you see that phrase, that should be the first thing you think. Then what I do over here to the side is I say, okay, what is x1, y1, and the slope? Well, they give you x1 and y1 because it says through the point 1, 1. So I know x sub 1 is 1. I know y sub 1 is 1. How do I know the slope? Or how do I find the slope? The derivative. And didn't they already give you the derivative, dy by dx, in the original problem? dy by dx is just xy over 2. So 1 times 1 over 2 is just a half. So now, my equation of a tangent line is y minus 1 equals a half times x minus 1. The nice thing about free response items is you get to stop. You don't have to worry about whether it's written in slope-intercept form, or point-slope form, or general form. Once you get it in point-slope form, you're done. You can stop. In fact, if you go on and you make a little tiny error, they won't give you that point. But if you stop here, you get full credit. So I beg of you to leave it in point-slope form. Leave it in this form. All right, so that's the first part of part B. The second part says use your tangent line to estimate f of 1.2. Well, what does f of 1.2 mean? You're plugging in 1.2 for x and solving for y. So I say y minus 1 equals a half times 1.2 minus 1. And believe it or not, you may leave your answer like this and get full credit. All I did is I subbed in 1.2 for x and I got y by itself, and then I just stopped. They have to give you full credit if you have y by itself. Now if you do this, you don't get full credit for this line. But if you get y by itself and you just didn't simplify numerically, you have to get full credit for that, okay? Turns out, we're going to figure out what that is because we need it later. We need to know the numerical value later. So if you do this computation, it turns out to be 1.1. Because this is just 0.2 times a half, 1 half times 2/10 is 1/10, and 1/10 plus 1 is 1.1. Again, they have to give you full credit for this, but we're going to be using this value later. That's why I had you go ahead and compute it. So part C was from the beginning of the semester, right? The equation of a tangent line, right? There wasn't anything groundbreaking or earth-shattering about part B, other than the fact you may not have been thinking that because you see the slope field problem, and then that's how the free response items work. They'll have multi-steps, and they might ask you about the tangent line in one part, they might ask you to graph the slope field in another part, and then you might be finding the particular solution by separation of variables in another part. So your mind, you know, you have to go all over the place and pull things from all throughout the semester. All right, part C says find the particular solution y equals f of x to the differential equation with the initial condition f of 1 equals 1, and then use your solution to find f of 1.2. What does that tell me to do? Particular solution. What does that mean? Separation of variables. Particular solution means here's the derivative, figure out what the original equation was. This time it's not so easy because we have dy by dx equals, what was it, xy over 2. And so to find the particular solution, we not only have to get y by itself, but we also have to figure out what c is, using the order pair, or the initial condition as they call it, f of 1 equals 1. So don't worry about this until you have your c. Once you have your c, then you can sub this in to figure out what c is. So let's separate our variables. Usually what I like to do is cross multiply if I have a fraction equal to a fraction. You don't have to do that. But I like to write it as 2 dy equals xy dx to get me started. Then I need to move this y over to the other side. Get all my y's on one side, all my x's on the other side. So, everybody okay if I say 2 times 1 over y dy equals x dx? Why'd I leave that big space? Because I'm going to put the integral symbol in there to save me some writing. So now I'm going to take the integral of both sides, now that I have my variables separated. And so what is the antiderivative of 1 over y dy? Good. ln of absolute value of y, because it's u prime over u, equals the antiderivative of x is just x squared over 2, and I need to put a plus c on either side, but not both. So I choose to put mine on the right-hand side. We do have to do the e thing. Yes. And here's where it gets more complicated, isn't it? The algebra part, getting y by itself. Before we do the e thing, we're going to do an algebra 2 thing. Well, we could divide by 2, actually, if we wanted to. Another option is to move this 2 up to the exponent, and that way I get rid of the absolute value. But dividing by 2 is perfectly valid, and you will still get the same answer, okay? Just so you know.
If you do it right.
If you do it correct. All right, let me pull down some more paper here, and I'll leave those last few lines up so you can see it. All right, so I'm going to write mine as ln of y squared. I no longer need the absolute value because I'm squaring my y, equals x squared over 2 plus c. Now, before I go any further, I'm going to figure out what c is. You can actually do it at any point. I could do it here. I can do it here. I can go ahead and get y by itself and then do it if I want to. I think earlier today I actually even did it at this step here. But what you're going to do is you're going to put in 1 in the place of y. ln of 1 squared equals 1 in the place of x. What is ln of 1? 0. They will do that to you on the non-calculator section, by the way, where you have to know that. ln of 1 is always 0. 1 squared over 2 is a half. So our c is negative 1/2. Now let me just say, if you would have solved for y first and then found c, you would have had a different c value. But our final answers would have been the same. Depending on where you decide to solve for c, your c values might be different, but your final answer should be the same. So negative 1/2 is my c value. I'm going to put it back in here. So I'm going to say ln of y squared equals x squared over 2 minus a half. Now I'm going to exponentiate both sides. Base e. On the left-hand side, e and ln cancel, leaving me with y squared. On the right-hand side, I'm going to write it as x squared minus 1 all over 2 up in the exponent of e, because I have a common denominator. Are you with me? Okay. Square root both sides. So y equals plus or minus the square root of e to the x squared minus 1 over 2. I'm actually still not finished, because as I just mentioned before, I have to decide whether it's plus or whether it's minus. And it's all dependent upon your initial condition. What was our initial condition for this problem? Yeah, it was 1, 1. All right, now, what you have to do is you have to look at your slope field. Now we skipped the slope field for sake of time, but I have it here that I want to refer to. Here's what the slope field looks like for this one. If you look at the point 1, 1, over 1, up 1, you see that point falls right here. It's not necessarily what the slope is doing there, but it's what that portion of the graph is doing. Above the x-axis, this is actually going to be the positive square root, and below the x-axis is going to be the negative square root, because it's a reflection across the x-axis when you stick a negative out front. So, because the point is 1, 1, we're going to choose the positive square root. If the point had been 1, negative 1, we would have chosen the negative square root because it's below the x-axis. Yes?
Could you just have subbed back in 1 and 1 and then pick which one
Made the slope?
I just subbed 1
Wait, where were you going to sub it in?
to the y equals plus or minus square root e to the blah 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 blah. You sub it in.
Oh, sure. Yeah.
0
Yes.
e to the 0.
Absolutely. Yeah, absolutely. That would be fine as well. If you actually substitute the point in there, that would work. Good. All right, so we're going to use the positive square root. So make sure you state that. And then I always box in my answer. Doesn't have to be boxed in, but it sure helps. You could circle it, that's right. Okay, now it says use your solution to find f of 1.2. So we're going to substitute 1.2 in here. And we can use our calculator. So we're going to do the square root of e to the 1.2 squared minus 1 all over 2. Got it. Thank you. All right. If you round to 3 decimal places, which we should, 1.116. So I'm going to say approximately 1.116. Now for part D, it says compare your estimate of f of 1.2 found in part B Part B, we got 1.1. In part C, we got 1.116. They're pretty dang close, huh? Now, for part E, it says, was your estimate from part B an underestimate or an overestimate? It was an underestimate. That's right. And where it says use your slope field, I want you to write this down and then I'll show you what I mean by it. Underestimate because the graph is concave down. Through the point 1, Okay, now let me show you what I mean, or I'm sorry, I said concave down, it's concave up. Concave up through 1. So let me show you on the graph what I mean by that. So can everybody see if I drew the curve through the point 1, that it would be concave up? That is tending in a concave up direction. Well, the reason it's an underestimate, and you don't have to write this down, I'm just explaining it to you. If you have a parabola, say, that's concave up, the tangent line to any point on that parabola is going to be underneath the curve, no matter where you pick the point. And your estimate is coming from that tangent line. But if it's concave down, where's the tangent line going to be? It's actually going to be above. So that would be considered an overestimate. If it's concave down, if the graph is concave down and you use the tangent line approximation, The tangent line approximation is an overestimate. If you have concave up and you use the tangent line, it's going to be an underestimate. And then the particular solution, that actually tells you what it is. That tells you what the value is. So the 1.116, even though we estimated it to 3 decimal places, that gives you the actual answer. Questions on slope fields?
Yesterday's a Hercules calculator. Would that be a?
On one, that, yes, I'm glad you asked that.
Because I don't know how.
On 2013 AB, on the first free response from yesterday, no calculator, believe it or not. And on 2012, number 2, that one was a calculator problem.
No idea.
Oh, hey,
I
guys.
find decimal without using a calculator. Were they
On the first one or the second one?
Were they in the
The
second?
second one was
It was
a
like
calculator
crazy
problem.
decimal.
And I'll tell you a way to tell if it's number 1 or 2. See, this was number 2 from 2012. Number 1 and 2 are always calculator problems. And then this one was number 5. So 3 through 6 are always non-calculator problems on the most recent exams. Now, if I go back to older exams, it's a little bit different. But on the most recent exams, that's the case.
How far down is considered most recent?
Let's see. I think they changed it probably somewhere between 5 and 10 years ago. So if I give you like an
If it's
exam
10 or above,
question,
you're
yeah.
good.
And the only difference is those exams before they had 3 calculator, 3 non-calculator. So 1, 2, and 3 were calculator, 4, 5, and 6. So it's really just the number 3 we have to differentiate between what year it is. But also when we start doing these reviews, if I give it to you on colored paper, that means calculator. White paper means non-calculator. When we start actually getting into the review in January.
Oh no, I'm getting the code.
Okay?
Calculus is already.
It will be very, very obvious. Questions on slope field? So the only thing new, honestly, the only thing new today is the easy part, right?
Yeah,
No.
but it's the hard part that we're.
It's the hard part that's really hard though, that we've already seen. You need more practice with. The particular solution, the writing the equation of a tangent line, all that stuff. So for homework tonight, I've taped this for you guys, by the way. For homework tonight, what you're going to do is you're going to complete this sheet for me. So you have to do number 8. You got to do the slope fields on the front, and then also number 75. That worksheet I gave you, number 75. That has to be done. Needs to be done tonight as well. Tomorrow we'll talk about theorems.
Hey, there's our final.
Wednesday, Thursday, we'll go over some of this homework stuff if we get finished with our notes tomorrow. Final exam.
This is like halfway blessing and halfway curse.
Is this for the final?
This is for the final exam.
All we have to do is
Oh,
like,
I think I gave you.
all we have to do.
Yeah, all
is
we have to
memorize
do.
all-
All you have to do.
Everything.
Oh.
What you're saying is we get this in the final exam?
No.
That'd be better.